We are all here now, so I will officially start. Good morning, everyone. I think everybody's in morning now. No, some people are in afternoon. Well, I start this master thesis defense session introducing my master student, Renan Luigi Martins Baresi. Renan is going to present his thesis entitled Augmenting Analytics, Use Case Studies of Situated Data Visualization Towards Decision Making. I thank the telepresence of the members of the thesis committee, Professor Regis Copper from the University of North Carolina in Greensboro, Professor Veronica Teichert from the Federal University of Pernambuco, and Professor João Comba from our institute here at UFRGS. So thank you for accepting this task in such a terrible year. We also have the telepresence of Per-Erik Andersson, Slavomir Novacek, and Wagner Ulrike de Moraes, who are from the University of Halmstad in Sweden. They supervised Renan in his sandwich stage there that lasts for 5 months, plus 1 month for coronavirus lockdown. And I also thank the audience. So for those who don't know how our system of defense occurs, it's in 3 steps. First, a presentation by the candidate, about 40-45 minutes. Then we go to another step, that's the questions by the committee. And there's no time limit there, but most cases, each committee member spends 10 to 30 minutes or something to make their appointments. And in the third step, we go for a deliberation only with the committee. So I'll create a breakout room from this system and we can discuss and decide. And then we come back to give the results. So that's how it happens. So without more delay, let's start. Renan, it's with you now.
Good morning, everyone. Thanks for not coming over to my house today to listen to my presentation. I'm going to talk about my master's dissertation. It's called Augmented Analytics, Use Case Studies of Situated Data Visualization Towards Decision Making. As an introduction, I'm going to start talking about data visualization in a map context. So it's usual to have maps in larger scales, such as these two here, where you can see a whole country with data from different states, or a whole state with data from different cities inside the state, or even from a city with data from different streets. This here is a traffic data visualization, and this one is for COVID cases. So we can also do the same thing in a smaller scale. Here we can see a building fire evacuation plan, so you can have data inside a floor building. And here there's a bathroom floor plan where you can see data placed in a map for a small bathroom. So we could do the same thing in these smaller scales with augmented reality. And this is what I'm going to talk about today. So the first part of my work is called, well, it's not called that, but it's about decision making in seat choosing tasks. So for this part, we're going to analyze classroom data. So the main motivation and objectives for this was to explore ASV, that is Augmented Situated Visualization, as a concept, to expose the effect of ASV on decision making whenever it's compared to traditional 2D map visualizations, and to design and implement an interactive visualization of seat data in a classroom in order to help people to choose seats for them to sit at. So regarding data visualization in augmented reality, a lot of works are not situated, so they're just displaying data wherever in space. The data is not exactly there's no reason for the data to be there. So in this case, we can see molecular particles. It's just laying around in the environment. Some other works are focused on conceptual definitions without actually displaying an application or implementing anything or testing anything. And finally, there are some few applications where they actually test actual interfaces for augmented reality. In this case, there was a product visualization in a market environment where you could see nutritional data facts about the products. In this case particularly, there was an user study, but it wasn't that thorough, and the comparison was just between their implementation and actually reading the box, which is not exactly fair. Okay, so for our visualization here, we're gonna present both an augmented reality visualization and also a 2D map visualization. This one was done solely for comparing the two of them in order to get as fair of a comparison as we could, seeing the same data with the same elements. So in this first one, we could see a visualization for airflow in a classroom. So if you wanted to sit closer to where the wind is blowing more, you could analyze the data there. This next one is for people circulation. So if you wanted to sit where no one or less people walk in front of you doing the presentation, you could analyze the data. And this last one is for special seats. So if you're looking for a seat with a hearing aid or an extra wide seat or a left-handed desk, you could look at this data. These are just 3 examples out of some we managed to do. For the interaction part, on the augmented reality approach, we used a hand-guided virtual menu. So you could, whenever you looked at your hand, you'd see the menu, and you could select one of those or multiple of those options, and you would filter the data being visualized. You could select those by doing an air tab gesture, which is basically doing like this. And a similar interactive menu was done for the tablet for the 2D map version, and it's just a simple 2D menu. Here we have a video demonstration, and I'm gonna load up the video from YouTube here in a second. Okay, hopefully you can see it. It's just a demonstration of the data in an egocentric perspective. We use the HoloLens for this, the augmented reality headset, so the person would see all of this in first person. Okay, it was just a small video because we don't have time for the whole things. Oh, I clicked on the wrong place here. Here, okay. Great. So for our user study design, we separated the attributes that could be chosen, these ones, into 3 categories: scalar scores, vector routes, and categorical scores. And we divided these into a series of tasks for people to perform. These tests were 6, and they would scale in complexity, following the dual process theory of cognitive science, where you could have tests of type 1, which are more straightforward and easy to perform, and type 2, which are more complex and more thought-provoking. So we would use only one of the attributes per task in the tests of type 1, and on the tasks of type 2, you would have a combination of them in order to make it more difficult to choose a seat. So in these tests, for example, we would ask the person to choose a seat with the highest temperature, where there would be the least amount of people circulation, and that you would be close to a power outlet. So that's an example of a task there. None of the attributes is repeated in the same platform for a single user in order to avoid learning bias. The order of the attributes in each category was sorted among subjects to minimize any pattern repetitions. 2 different data sets were used for each attribute in order for us to minimize learning bias too. And the data sets and the platforms tested were alternated in a Latin square among the participants to avoid pattern repetitions. So for the results, we had 16 subjects participating, 7 female, 9 male. All of them claim to regularly use touchscreen devices, and only 18.7 used some augmented reality head-mounted display, such as the HoloLens, for example, at least once a week. So given these difference here, in order to minimize the previous knowledge bias, we made a short tutorial for people to be familiarized with the HoloLens. For the objective results in this test, one of the things we measured was the amount of steps, walking steps people took around the room. And here you can see that the test with the HoloLens required 13.5 less walking steps, and this was a statistically significant result. Also, in the accuracy aspects of the choices, people had an average of about 4% higher accuracy using the augmented reality approach when compared to the 2D one, but this was not a significant effect statistically. For the subject results, the 2D maps did get better scores for all 3 of the attributes that we measured: usability, simulation sickness, and workload. But at the same time, the ASV scores were decent, were acceptable. Regarding the results, we can see that screen-based visualizations since they are more commonly used, they can be considered a gold standard for this sort of task. Although we had acceptable subjective results, the augmented reality visualization still felt more like a foreign concept to most of the users. Regardless of that, our approach still surpassed the 2D visualization in most of the user performance aspects measured, such as the walking steps and the accuracy. Okay, so we're going to follow through to the next part, which is focused attention in outdoor path following tests, so following GPS routes, basically. The main motivation here was to explore ASV in the outdoors, to expose the effect of ASV on focused attention, so to see if there was an effect on the level of attention to people trying to follow a route, and not to cause any accidents or something like that, and to design and implement an ego-centric visualization of GPS routes, which arguably could help people to better locate themselves. Okay, so the problem statement in a 2017 survey, out of 158 accidents which were studied relating to personal navigation devices such as a GPS, 24% of those regarded missing road characteristics, so the person wasn't paying attention to the road. And among 44 of those, there were deadly accidents. And 21 of those involved distraction in some sense, so the person guiding the vehicle was distracted. About the related work of this field, a 2017 study implemented a situated augmented reality navigation visualization, but it's only in the indoors, so people would follow routes inside of an office environment. And a 2011 study, there was research much like ours, but it was purely simulated. So the users weren't actually guiding vehicles or walking outside. They were just using a simulated driving platform in virtual reality. So for the design and implementation, we use the Google Maps API in order to get the routes and the maneuver waypoints, so steps of the way where you would be asked to take a turn or follow through on a roundabout. On top of that, we also had to use the Android platform to get the GPS location and to get a calibration of the magnetometer in order to actually make north point to the Earth's actual north. Here I'm gonna show you another quick video. Second. Okay, there's sound here, but you can mute it if you want. It's just a sound. So you can see that the virtual holograms here jiggle a lot. That's because the HoloLens struggles to track the environment outdoors, especially because the visual details are more far away and sometimes it's too bright. Okay, I'm gonna pause it now just to save time. Okay. Regarding the user evaluation, we compared the ASV approach to a 2D map on a smartphone using Google Maps. The same route was made for both platforms. We just alternated the order of the platforms and the beginning and end of the route between users. The route was to be made on foot in order to avoid any accidents, since it was only a prototype. As a result here, you can see that all subjects using the ASV managed to get through the whole path. 12 users took part on it, 2 female and 10 male. The GPS data, the time, and the focused attention levels were measured. This last one was using an electroencephalogram headset, which has a little sensor on your forehead that measures brainwaves. And after each trial, users answered the SUS and the NASA TLX questionnaires. That's for usability and workload, and another original questionnaire adapted from another study. So for the objective results, on average, people took about a minute more or less than a minute more to complete the path using the ASV approach. And regarding the focused attention, our approach demanded a significantly less focus demand than the 2D maps. Regarding the subject results, the 2D map platform again got better results, but that's basically a given because it's a platform everyone uses almost daily, some people at least. And but the ASV still got decent scores. The usability was a C grade, which is not great, but still acceptable. And regarding the original questionnaire, we got questions like safe to use, support for navigation, fun to use, and route attentiveness, and traffic visibility. And our implementation got better results in these last three. So people regarded it as having more higher traffic visibility and a better route attentiveness, besides being more fun to use. So regarding the results, SV navigation objectively worked. All subjects reached the destination in time. The road traffic and route visibility were higher in the ASV approach, so people actually felt like they could still see the road, the traffic, and the route at the same time without impeding them to follow the route and to pay attention to the road and the traffic. The ASV demanded less attention according to the EEG headset, which allows them to perform a primary task such as paying attention to walking or driving a car or riding a bicycle. And the subject results indicated what needs to be worked on for future research and development if in sometime in the future this comes to be an actual product, commercial product. And the current available augmented reality head-mounted displays still lack the components for a better usability and a lesser cognitive load demand for outdoor tasks, at least. So now onto the final part. This was focused on interaction and visualization methods for data extraction in EMC, which is electromagnetic compatibility. The main motivation here was to explore ASV in an industrial environment, to expose the effect of different ASV in both interaction and visualization methods on data extraction tasks in this environment, and to design and implement freehand interaction techniques, which in order to minimize the need to touch different devices or surfaces, which is actually relevant nowadays, since we're all trying to avoid touching different things. The problem statement here, according to Paul, in a book from 2006, a system can be considered electromagnetic compatible with its environment if it does not cause interference with other systems, if it is not susceptible to emissions from other systems, and if it does not cause interference with itself. So here we can see an example of someone using an electric shaver. This shaver emits electromagnetic radiation, which causes a television signal to be messed with in a nearby room. So another person gets affected by that. Regarding the related work from a study in 2018. I'm only gonna talk about now works that analyzed data visualization in EMC in augmented reality. So this first work here, it was a 2D situated visualization. It can be considered situated, but it's actually only a heads-up display. So it's only like a small screen set on a part of the user view, and it only displays 2D graphs. This next one, it is actually situated on the actual space, but the data is actually really discrete. It doesn't really portray an actual electromagnetic field. You can really picture it, and it also requires markers to place the data on the actual location. And this final work, to meet the most complex one of these, it focuses on small scale 2D grid readings, and it also lacks a user study. So their objective was to make a device that could read the data on the go using a cell phone and a chip here. But it can only be used on a small scale. So for our implementation, we decided to go with a room scale EMC visualization. In order to accomplish this, we used an anechoic chamber, which is commonly used to make EMC spatial measurements of devices and setups. So it's like a big chamber padded in order to avoid echoes for both sound and any electromagnetic wave. And it's also a Faraday cage, which keeps it from being interfered with outside radiations. In order to actually place the data inside the room, we 3D scanned the whole chamber into a mesh to facilitate this, placing everything spatially inside it. This larger scale that we chose to follow was in order to aid in perceiving the effect of electromagnetic interference in the environment. So whenever you have an antenna here or any device that you're taking measurements from, you can expand these data towards all sides, and you can see how it affects other components inside the same environment and with which intensity. Okay, so for the data visualization, we decided to go with two different approaches. The first one was a 3D field topology, so we're drawing the whole field around the measured object. We did this by converting the data read from the intensity data read from spherical coordinates, which is how they are presented by the chamber system, into Cartesian coordinates in order to place them on the environment. This topology is based on these different topologies here are based on multiple frequencies that can be compared by overlaying different color-coded meshes. So here you can see an orange and a blue one. So those are measurements made with from different frequencies, so you can compare them on the go. And you can also scale the field in order to perceive how it collides with the environment. So if you have here you have a computer setup. So if you were to see how this affects with another computer placed on another place in the same environment, you could scale it up in order to see how it affects this other environment, and you can read the data, the intensity data at that place. There's another piece set of data that you can analyze in the chamber. These are faster readings, and they are done as planar sections of the field. So you only get a horizontal planar section. And we decided to go with 2D color-coded raycasts. So these were drawn as vectors extending from the center of the device read until infinity, or until occluded by another surface or another device, and these occlusions represent collisions with them. These raycasts are color-coded according to the field intensity at that point in place. And the color also fades accordingly to the intensity as it fades away. Okay, so in order to allow users to extract data from these visualizations, we decided to go with three different data extraction methods. The first one we named hand slider. It's focused on more precise measurements. So in this one, the user would choose one of the lines in the 2D visualization, and at the place that they chose a point in the line, there will be a small measurement panel here where they would see the values, and they could, with their hands, put it to one side or the other in order moving the panel along the line in order to take different measurements from the data. This next one we called gazing. It focuses on quick measurements that can be made from a distance, which can require less movement from the users. And it's similar to the last one, but instead of using your hand to move the cursor or the panel along the line, you can use only your head. So you would move your head to one side or the other, and this would move the panel along the line, taking measurements. This final method was called touch lens, and it was made to be a more straightforward method for people to maybe feel more comfortable with. It uses a touching metaphor. So instead of using a cursor from afar, the cursor is now your hand, and wherever you place your hand in the data, you're going to see the panel there, and it's going to take a measurement from that exact place. Here I'm going to show you a video demonstrating these techniques, both visualization and interaction techniques. So this first one is the 2D color-coded raycast. You can see that it stays in place on the height that it was first measured from, and it goes through until it hits a wall. This is the 3D field topology visualization. The color lines there are from the 2D ones. So it's just to show that you can see all of them at the same time if you want. And you can see multiple frequencies too. Okay, so now for the interaction methods. This first one is the hand slider. So the user is going to place the panel there, and with his hand he can move it along the line. The idea here was to track that cardboard box, which was the target. This is the gazing one. So here you don't need to use your hand. You can use only your head and move your sight at different places, and that's gonna move the panel along the lines. This final one's the touch lens, so you can use your actual hand to place the panel on top of the field. It works both on the 3D and the 2D visualizations. So wherever you place your hand, there's going to be a reading from that place. Okay, so I'm going to go back to the presentation. Okay, so for the user study, we went with 9 different data extraction tasks per method tested with the users. So in each of the methods, users had to go through 9 data extraction tasks. A prop antenna was used with real EMC data situated around it. So the data is actually read from a real antenna. The antenna was just, but it wasn't this actual antenna. This was just used as a prop. And 10 different targets were placed around the room in order for users to make measurements at their locations. These targets were cardboard boxes. Regarding the interaction test, we divided the tests into 2 parts, the interaction and the visualization. In the interaction test, the interaction method was used as an independent variable, so we would go from one to the other. And the visualization was fixed as the 2D color-coded raycasts. For the visualization test, the opposite was done. The visualization was would be moved from the 2D visualization to the 3D topology vis, and the interaction was fixed as the touch lens. In order to minimize any learning bias and avoid pattern repetitions, we used Latin squares, and in order to alternate the methods and the targets being used by the users. As for the results, due to the current pandemic situation, the number of participants in this particular study had to be limited in order to provide proper spacing in time between the tests, to follow on social distancing protocols and sanitization of the equipment in the room. Only 5 users took part on the test. 2 were male, 2 female and 3 male. Only one claimed to have had any familiarity with augmented reality hand-mounted displays. The number of walking steps, time, and the error ratio was measured for each trial. And after each trial, users would answer the SUS, the NASA TLX, and the SSQ, the Simulation Sickness Questionnaire, and also a presence questionnaire based on another work focused on augmented reality. So for the results, the amount of walking steps in the interaction task, the gaze technique had the smaller amount. For the visualization test, the 2D visualization had demanded a lesser amount of steps for people to make the measurements. Regarding the time, the 2D touch lens technique required by far a smaller amount of time than the others. And regarding in the visualization test, the 2D technique again had a considerable smaller amount of time. Regarding the intensity errors between the ground truths and the ones given by the users, the hand slider technique was the most accurate. And for the visualization test, the 3D actually got the most accurate results. On regarding the subjective results, all 3 of the interaction methods got decent results. The gaze and the hand slider got better ones for the usability. And regarding the visualizations, the 3D visualization got actually a pretty bad score, and the 2D one got a decent one, although it could be better. Regarding the simulation sickness symptoms, only the gaze technique demonstrated to have any significant symptoms. All of the other ones were negligible. And regarding the visualization, again, both cases presented negligible symptoms. For the presence and perception questionnaire, the hand slider here demonstrated to have a higher realness, and a higher spatial presence, and a smaller perceptual stress to users. So people felt like the virtual elements here were more real. They felt like they were more spatially present in their environment, and they had a less stressful time with their perception of the data. The same goes for the 3D visualization. They felt like it was more real, it was more spatially present, and it had a lesser perceptual stress demanded from the users. Regarding the workload, all three got acceptable results, with the 2D touch lens having the by far the most acceptable workload, demanding less from the users to perform the tasks. And the 3D method, regarding the visualization methods, required quite a lot more from the users to perform the results. Okay, so as for the discussion of the results in the interaction aspects, there was a statistically significant effect regarding the different interaction methods used on all three of the variables measured, walking steps, time, and the error ratio. The gazing method demonstrated to require the least amount of time, and the least amount of user dislocation. This could be explained since the gazing method allows users to perform readings from a distance. The touch lens technique took the least amount of time to complete the tasks. This is likely because it was the most straightforward method, so people learned it more easily. And the hand slider method helped the users to commit the smallest error ratios. This was again likely due to users being more used to perform refinement tests with their hands, since humans are used to do precise fiddlements with their hands. Regarding the visualization results, there was a statistically significant effect regarding the visualization methods used on only on the error ratio variable measured, so the other ones were not statistically significant. The 3D topology exposed results that helped users to commit the smallest error ratios. This is possibly due to users feeling more free to make the readings, since they weren't restrained to a 2D plane. And the 2D raycasts visualization required the least amount of walking steps and also time, but these results were not statistically significant. Okay, so for the general discussions, conclusions, the three different ASV use cases were implemented and presented, as well as how they impacted those particular scenarios in decision-making tests performed by in-user tests. Both current and traditional interaction methods were adapted into augmented situative visualization, always focusing on freehand gestures. Arguably, the main advantage of ASV against an allocentric representation is not requiring a mental translation from the 2D visualization into the physical location surrounding the users. And the proposed applications expose compelling results in their favors. As for the main contributions of the works, augmented reality interfaces for analyzing data situated in loco were deemed as a valid and promising solution in three different contexts, exposing acceptable scores in usability and workload. In the seed choosing tasks, a gain was noticed in choice accuracy, and fewer walking steps were recorded for the ASV comparison with 2D maps. In the outdoor path following tasks, ASV demanded a lower attention focus level than the 2D counterpart, and in the EMC context, a precision time trade-off for different interaction methods was exposed, suggesting that specific techniques can be chosen based on different task requisites. So for the limitations in future work, the HoloLens hardware was used. It has a limited screen size, at least the first generation. It has a limited processing power and arguably an inability to track outdoor spaces. It lacks better hand tracking. There is no hand occlusion, and only simple gestures can be made. Regarding the HMD paradigm as a whole, it is still a novelty and a foreign concept to most users. It still feels heavy and uncomfortable for most users too. And as for the lack of statistical significance in some of the results presented, there's a need in future works for a bigger population size and or a more complex and thorough set of tasks. Regarding studies in other application of ASV, we propose as future study the spread of breath particles in the air and surfaces at local gatherings, which is actually really relevant nowadays with the whole pandemic, and the presence of radioactive particles atop surfaces on nuclear power plants and hospitals. I included here a slide that besides the dissertation, I had some other publications and presentations done, some posters and some contests, participations in conferences. And that was it. Thank you everyone for not coming here today again, but being available to hear me. And I'm available for questions.